For this exercise, verify that the metric components satisfy the coordinate transformation rule for tensor components when transforming from Cartesian to polar coordinates in the Euclidean space R2. In Cartesian coordinates, the metric components are given by g11 equal to g22 equal to 1 and g12 equal to g21 equal to 0. According to the coordinate transformation rule for tensor components, the elements of the metric tensor in polar coordinates should be given by g rho rho equal to dxi d rho dxj d rho multiplied by gij. G phi phi should be given by dxi d phi dxj d phi times gij. And finally, g rho phi by symmetry should be equal to g phi rho and given by dxi d rho dxj d phi gij. Looking at the relevant partial derivatives, we have that dx d rho is equal to cosine phi, dx d phi is equal to minus rho sine phi, dy d rho is equal to sine phi, and dy d phi is equal to rho cosine phi. Inserting this into the transformation rule, we find that g rho rho is given by dx d rho squared g11 plus dy d rho squared g22, where both g11 and g22 are equal to 1, and inserting the expressions for the partial derivatives gives us cosine squared phi plus sine squared phi, where we use a familiar trigonometric identity to conclude that this is equal to 1. For the phi phi component of the metric tensor in polar coordinates, we obtain dx d phi squared g11 plus dy d phi squared g22. Again, using that g11 and g22 are equal to 1, this is equal to rho squared multiplied by sine squared phi cos squared phi, which again is equal to 1, so this is equal to rho squared. For the off-diagonal components, g rho phi, which is equal to g phi rho, we find that this is equal to dx d rho times dx d phi g11 plus dy d rho times dy d phi g22, which when inserting the expressions for the partial derivatives is equal to minus rho cos phi sine phi plus rho sine phi cos phi. And we see that those terms exactly cancel and we get 0. So this gives us the components of the metric tensor in polar coordinates. We see that the non-zero components are g rho rho equal to 1 and g phi phi equal to rho squared, which is exactly what we have previously found for the metric tensor in polar coordinates. And we can therefore conclude that the metric components indeed follow the correct transformation rule for tensor components.